So good afternoon. We have the Oliver Schlotterer talking about combinatorics on words in string amplitudes.
Yeah, thanks for the introduction, Matteo, and big thank you to the organizers for setting up this meeting and giving me the opportunity to speak. So in choosing the subject and scope of this talk, I took the word combinatorics in the title of the meeting very serious. So I tried to tell you some stories from the realm of string amplitudes, where I see particularly high connectivity to combinatorial structures. I will draw material from various references. So here is an extremely incomplete list. Just approach me to ask for more targeted references. And for instance, the uppermost reference is a review. So different people in the room may have different focus. So just consult me on which sections in the review might be best suited. And then the middle reference, this is work of Hedley Frost. It's a particular pleasure to give the talk in front of Hedley in the audience, who wrote a beautiful paper with Carlos Mafra and Lionel Mason about one of the combinatorial protagonists in this talk, namely the so-called S-bracket. And yeah, some of the results towards the end of the talk are about work in progress, also involving Hedley Frost and Carlos Rodriguez, who is a postdoc in Leipzig in Bern's group. Yeah, so the goals of the combinatorial gadgets in this talk include efficient handle on multi-particle amplitudes. Typically, multi-particle means more than 4, where it becomes important to have a good way of bookkeeping the multitude of external legs, where you don't want to drown in the combinatorial complexity. And another goal, which I'm not sure whether I can fully convey this within the 1-hour format, is that the combinatorial structures to be discussed, they are pretty universal in the sense that, first of all, I will motivate and illustrate them from field theory. Non-abelian gauge theory or gluon scattering amplitudes in Young-Mills, this will be a first instance. And one way to think about string amplitudes is that they augment gauge theories of point particles to now depend on a length scale, or more precisely alpha prime being somewhat the square of a string length scale. And I will argue that the combinatorial structures from the gauge theory will uplift to all orders in this alpha prime string length square. And even though I don't expect to have time for loop level, let me nevertheless give you the promise right here that the combinatorial structures do have a strong echo beyond tree level. Though admittedly, most of the equations you will see are about string tree level, leading order and perturbation theory. Yeah, so the outline, I think I more or less said it already. We will start in Young-Mills field theory. I will tell you about a shuffle product governing certain amplitude relations known under the name Kleist-Coyve. Then I will tell you about different amplitude relations in field theory attributed to Bernd, Carrasco, and Johansson, and will give a reformulation of these BCJ relations, which not everybody may have seen, using the so-called S-bracket, one of the key combinatorial structures. Then after this field theory setting the stage part, we will move on to string theory. I will start with gluon amplitudes in heterotic string theory, where the gauge sector comes from closed string vibration modes. And we will see an immediate uplift of these shuffle and S-bracket structures to gluon tree amplitudes in the heterotic string. Then we will go into halfway integration business. I mean, in string theory, already tree amplitudes have a lot of non-trivial integrals for you. And I will argue that the S-bracket will play a prominent role in doing these integrals in string tree level, namely to work out alpha prime corrections, what goes beyond field theory. It's good to have the S-bracket on your side. So if you really play these number theory games to the very end, you will get multiple zeta values. But I try to only focus on the combinatorially relevant aspects and leave the number theoretic discussion to the afternoon team. Okay, and as far as time allows me, I will give a loop level outlook. Any question about the overall plan? Okay, then let's start with introducing the shuffle product in the context mostly of gauge theory amplitudes. I will be agnostic whether we are talking about pure Young-Mills or some supersymmetric variant, because for the gluonic amplitudes at tree level, it doesn't matter whether there is an S for super or not. And to make sure all of this is proceeding in a mathematically tidy way, let me give careful definitions, starting, for instance, with a vector space of words that I want to consider. So the advertised combinatorial structures operate on a vector space of words, or more precisely, linear combinations of words in some alphabet. Oh, and most importantly, we don't like repeated letters. I mean, the letters, to give the spoiler straight away, the letters will be enumerating external leg number 1, external leg number 2, external leg number k. These will be the letters. And needless to say that in an amplitude, they don't appear repeatedly. And here, this A in the vector space of words refers to the alphabet. Oops. A, which is some subset of the natural numbers. Typical labels you give to the external legs in an amplitude. Never ever. Yeah. So just to give you a feel, so typically words are denoted by capital letters like P. And then here I have several letters I1, I2, all the way to I. And to encode the length of the word, I will sometimes take the liberty to put the P into vertical bars, the P referring to the word in this W of A. And yeah, clearly these letters I belong to the alphabet. Good. And yeah, on this WA vector space of words, let me define for you the shuffle product. I'm sure that many of you have seen this before, so my apologies if this is a bit boring to the experts. So the shuffle product can be defined in a multitude of ways. Here I give you the recursive definition. Namely, suppose you deal with very short words, for instance, the empty word, then shuffle does nothing at all. Shuffling the empty word from either the left or the right into a generic word P does nothing. So this is the initial value for the recursion. And now if we want to know the shuffle of non-empty words on both sides, I can do this recursively in the number of letters. So I'm exposing the leftmost letter I and the leftmost letter J in this concatenation here. So this is a composed word starting with I and then all the letters that may be contained in P. And I can peel off the leftmost letters using this rule here. Okay. And yeah, as you have probably guessed, that's applicable to all kinds of letters in the alphabet and words P and Q. Yeah, at an intuitive level, this is nothing but going over all possibilities, how you can shuffle decks of cards. So here is word P, namely an ordering of cards. Here's another word Q, yet another ordering of cards. And we shuffle over all possibilities to shuffle them in a childish way. This is what that product here does. Okay, now having set up that shuffle product, I can tell you something about Young-Mills tree amplitudes. So in the first place, the external states in Young-Mills depend on a lot of things, including gauge group generators of UN, the capital T's up there, or nickname color degrees of freedom in physics jargon. And we don't like it that there are so many variables entangled with one another. So we organize all the dependence on color, namely these T generators, in terms of traces. So at tree level, these single traces is all there is, at least in field theory. And then the coefficient A of the given trace, well, it by definition no longer depends on color. and we call this a color-ordered amplitude. And this is not permutation symmetric, this A, with respect to the letters in there, but you need to be careful about the cyclic permutation rho up there. And it will have, at the very least, a cyclic property, given that it describes the appearance of a trace. Well, since a trace is cyclic, so will be the coefficient A, the color-ordered amplitude. So there is a maximum of n-1 permutations if all you know about A is cyclic symmetry. But this is not the end of the rope. After cyclicity, there are some more relations, and the first bunch of them is known under the name of Gleise-Kauf. Sorry if my Dutch pronunciation is not that good. Let's just say KK to be on the safe side. So KK relations among color-ordered Young-Mills trees. Well, it's a very old story known since the 80s. And if I want, I can summarize KK relations as follows. Suppose I do n external legs. Say the last leg, number n, is here at the end. And now I get a relation by inserting a pure shuffle of non-empty words, P and Q. So if this is applicable to n points, then this means letters 1, 2, ... n-1 need to be distributed into these words P and Q. And most importantly, keep them non-empty. And I forgot the most important statement. This shuffle of Young-Mills trees is 0 whenever P and Q are non-empty. So this gives you a bunch of relations going beyond the cyclicity. And if you excessively write them down, then at n points, there can be at most n-2 factorial color-ordered amplitudes. For instance, you can enforce your favorite pair of legs to be next to each other, and then the remaining n-2 legs can do whatever they want. Yeah, and in some guys, KK relations have been highly present in many, many talks of this week, namely our beloved Park-Taylor factors obey identical KK relations. And let me specify this in a particular version of Park-Taylor's. I think the majority of Park-Taylor factors seen in this meeting were cyclic. And I'm already taking the liberty to send one of the legs to infinity. Or in other words, I'm not writing a cycle now, but instead I'm writing an open chain of such Zij factors where, similar to earlier speakers, I'm defining Zij to be nothing but the difference. Yeah, so for friends of cyclic Park-Taylors, imagine there is a leg Zn somewhere, and that one is sent to infinity. After dividing out by Jacobians, you arrive at this version of Park-Taylors, hence the little pt notation. Now, why did I jump from gauge theory trees to Park-Taylors? Well, I did so to point out the commonality that also Park-Taylors are annihilated by pure shuffles, again, demanding that both of these words, P and Q, are non-empty. Okay, so this is perhaps the first indication that this shuffle product wants to be discussed at the level of worldsheets, even though its oldest incarnation in amplitudeology appeared in the context of Young-Mills tree-level amplitudes. Good, and as I said, this was a first reduction of the color-ordered trees from n-1 factorial to n-2 factorial. But the experts in the room clearly know we can go much further. Only n-3 factorial of them are linearly independent. And it was Bernd Carrasco-Johansson who clarified this using their BCJ relations. And I will give a reformulation to those in terms of the so-called S-bracket. Okay, so the BCJ relations are from May 2008. And the first time they have been written in terms of an S-bracket-like gadget was in 2014. Okay, so what's meant with this term S bracket? Perhaps I first write down a somewhat bulky formula, almost as a provocation, to make it clear that we need to understand the combinatorial structure behind it. So a certain linear combination of Young-Mills trees is 0. Namely, a linear combination where I again leave the last leg n untouched. And now I sum a huge number of terms. Pick a word P, non-empty, please. Pick another word Q, non-empty, please. And now let's sum over all deconcatenations. Take P apart into a letter I and some words X and Y to the left and to the right. And do the same kind of deconcatenation with Q. And now the thing that vanishes is Young-Mills trees with, here is a shuffle of X into transpose of Y, where transposition means I reverse the order of letters. So, and then here are these letters I and J, which got isolated in the middle of the words P and Q. And then on the right of I comes another shuffle, namely with the remaining constituents U and V that were formed out of the word Q. Yeah, sorry for just throwing this definition at you, which admittedly may not look that inviting at first glance. There's also an alternating sign that I almost forgot, an alternating sign which flips with the number of letters in U and Y, the respective subwords here. Okay, so first step of unpacking that, let me give you an example. At 4 points, for instance, this intimidating formula is doing nothing than saying that this 4-point color-ordered Young-Mills tree is equal to its permutation, but there are some Mandelstam factors. Just to be clear, these Mandelstam's Sij, similar to earlier talks, are dot products of massless momenta. And I think my conventions are such that there's a factor of 2 baked in. Yeah, all the legs will be massless here. So the usual constraints coming from the fact that the pi squared to 0 also apply throughout this talk. Oh no, they are completely distinct. So the Z's are marked points on the Riemann sphere, and the Sij are commutative indeterminates whose prehistory is vectors pi in d-dimensional Minkowski spacetime. By the way, you probably won't see spinor helicity variables in this talk because everything is dimension agnostic. As a string theorist, I tend to be mostly at home in 10D, but you can, sorry. Yeah. Okay, they are by themselves functions of polarization, momenta, and whatnot, but you don't need to care. Just view these A's as black boxes. They depend on a word, modulo cyclic moves, and I'm telling you now some additional identities which are not yet visible from the fact that they are cyclic and not visible from the fact that they obey KK relations. So KK relations are somewhat simpler. The coefficients are plus, minus 1, and 0 if you expand out the shuffles there. Mm-hmm. It's n minus 2 factorial, or here I need to adjust. It's k minus 1 factorial in case of the Park-Taylor. Yeah. And you reduce the factorial by 1 more unit in additionally switching on the S bracket. I haven't done it for the Park-Taylors yet, but this will come in the next minutes.
Just to clarify about measures, so you can just impose KK relations.
Yeah.
So the space will be n minus, k minus 1 factorial.
K minus 1 factorial here and n minus 2 factorial in the A tree. Yeah.
And k is already n minus 1?
K is n minus 1 if you line up the formula with one another. That's true. These are additional relations which you don't get from KK. This is intuitive from the fact that there are extra Sijs, which were not yet mentioned in the KK blackboard. Okay. Yeah, so this formula here came from a specialization of P to be 1, 2, and Q to be 3. Okay, I admit this looks a little bit intimidating, so let's make sure we are giving a bit more intuition and or structure to this formula. So this formula here, these BCJ relations, are my motivation to introduce a definition of the S bracket. It's encoded in binary operation on words, known as the S bracket. Namely, I will use curly brackets to denote it, the S bracket. The curly bracket of words P and Q is defined in such a way that, yeah, these deconcatenation sums are captured from the formula for Young-Mills trees over there. So this time I'm putting the alternating sign here. And yeah, as before, Mandelstam invariance, tracking the letter I and J within these deconcatenations. And as you saw it within the A's, there's a shuffle followed by the letters IJ, followed by yet another shuffle. Okay, and yeah, so the properties of this S bracket, most of all the fact that it is a Lie bracket, this was discussed in the reference here of Hadley and Carlos Mafra and Lionel Mason. Now, I should be more precise on where exactly the words live that are inputted and outputted. So the P's and Q's here are only taken serious modulo shuffle. Namely, we are not just saying that they are elements of WA, the vector space of all words, but instead we are dividing out shuffles. So we are getting 0 result if P is a pure shuffle of non-empty words. So in that sense, this S bracket is only defined in this quotient space. So just to be clear, the thing I'm dividing out, this SHA, is all pure shuffles of non-empty words P and Q. Okay, and I hope many of you have seen this quotient space as being the dual to Lie polynomials. Okay, so the S bracket wants you to be in the dual space of Lie polynomials in both P and in Q. And likewise, the output should be understood within L star. Okay, so this is now the explicit definition, but perhaps it's an edge more comforting to do this recursively. So I can, instead of the lengthy explicit definition, give you a recursion. So for instance, in case you plan to at home code it and play with it, maybe it's also nice to have this recursion. For instance, suppose you want to eliminate 2 letters, I and J, from the first slot. You can do so by pulling out I and alternatively pulling out J. So in both terms, there are fewer letters than on the left-hand side enclosed in the brackets. And a similar formula applies to removing 2 letters from the second entry. And perhaps I should have referred you to these examples before. So some simple warm-ups for both the shuffle product and the S bracket are given right here. No. So you can view each pair of curly brackets as being linear in S. So I would have a problem if I were to write another S as a coefficient on the right-hand side. Yeah, and the starting point, just to repeat that here, the starting point, if we just have a letter in left and right of the comma, then it's just concatenating like such. and decorating with a Mandelstam invariant.
Let's have this as formal parameters. We need to impose relations that they like sum over J.
Oh, yeah, indeed, this will become relevant in the next section. So spoiler, just impose the usual Mandelstam invariance for momentum conservation and the fact that all the PIs individually square to 0. Just the usual kinematic phase space of n massless on-shell particles. Yeah. Okay, so this was the field theory prelude. I will now move to strings. And I guess one of the cliffhangers in the room is, if for KK relations, I could immediately give you a Park-Taylor prototype, you may also want to know if the S-bracket relation is somehow realizable using Park-Taylor factors. And well, if you meet Park-Taylor factors in empty space, they of course won't satisfy any S-bracketish relations. I need to tell the Park-Taylor factors what the Mandelstams are. And yeah, we have heard already many talks that the CHY formalism is one possibility to connect the marked points on the sphere within Park-Taylor factors to kinematic phase space. And alternatively, you can consult conventional string theories with alpha prime to give you a similar kind of coupling between marked points on the Riemann sphere and kinematic phase space. So this is the prelude to the alpha prime uplift section. Namely, we are still taking gauge theory states for the external legs, but now we are scattering Young-Mills states in the context of heterotic strings. Trees of okay, so again, I'm looking at color-ordered amplitudes at tree level. So this color decomposition up there is applicable both to Young-Mills and to string theory. Strictly speaking, the heterotic string even has a double trace sector, but I won't comment on this today. Just ask me if you want to know more about the double trace sector. Okay, and now for the single trace gauge amplitudes in the heterotic theory, I can give you a worldsheet formula. So the plan is to integrate over the moduli space of a couple of marked points on the Riemann sphere. So there will be as many marked points as there are external legs. And we can mod out by Möbius symmetry. We actually must mod out by Möbius symmetry if we want to make contact with the moduli space of punctured spheres. And I will do so by sending Zn to infinity and Z1 to 0 and Zn minus 1 to 1. And then all the other n minus 3 z's will be honest to God integration variables here. So I have n minus 3 complex integrations to do, removing the diagonals like such. Okay, so this is just a SL2 gauge fixed way of writing down an integral over M0n, the moduli space of n marked points on the Riemann sphere. Okay, now what is the integrand for these heterotic string trees? So I put color ordered ones to the left, so I must put the information about the color ordering P somewhere on the right-hand side. And the only place where this color ordering enters is through a Park-Taylor factor. Okay, and all the rest will be independent on the color ordering P. And yeah, what is this rest? There is a so-called Koba-Nielsen factor. All the differences, Zij, appear weighted by Mandelstam exponents. And then there is a permutation invariant object that I will unwind in a second. Before worrying what this object E is in detail, let me just say that it is permutation invariant and antiholomorphic and rational. Antiholomorphic in the Zi and rational. Yeah, so friends of the CHY formalism can immediately write this as a reduced Pfaffian. And in string theory lingo, this is essentially the correlation function of the supersymmetric vertex operators for the gauge boson. Or if you wish, it's the chiral half that tracks the dependence on the polarization vectors, but this won't be relevant at all. Okay, just to have the formula exact, there is a not so interesting prefactor, alpha prime over pi to the power n minus 3. Okay, so now these color-ordered amplitudes, I can ask again how many linearly independent ones there are. And at most, there can be n minus 1 factorial, already by their definition. But the BCJ and KK relations that we saw for Young-Mills trees, they actually carry over to the entire heterotic string amplitude, even its functional dependence on the alpha primes. I think the first time this was spelled out was in this Stieberger-Taylor paper from 2014. Yes, please. This one here. Oh, no, it's a highly involved function. It has poles at the origin, at finite locations. At 4 points, it's a ratio of gamma functions, which you may know under the name Virasoro-Shapiro. Let's better not get into a detailed discussion of the complete functional dependence, but I will have comments towards the end on the series expansion around alpha prime equals 0. So for the moment, let's look less into the part here of the integrand, but let's focus on the Park-Taylor factors. If the Park-Taylor factor obeys KK relations with respect to the ordering P, and if this is the only way how the right-hand side knows about the color ordering, then I can immediately be sure that the KK relation applies to the full heterotic string amplitude. Mm-hmm. Yes, on the nose, the Young-Mills tree will be recovered. Mm-hmm. Precisely. I mean, once you have computed this beast for a fixed choice of P, you can get all the remaining color orderings for free by relabeling the indices of the polarizations and momenta. And then, in that sense, you're done once you have nailed one color ordering, if you're willing to relabel by hand. But it can be quite interesting to expose certain symmetry properties and transcendental structures to know about the relations in between different choices of P. I'm sorry?
So where is it known where the poles of these denominator happens if di equals to dj?
Yeah, the poles will be regulated by alpha prime. So the kinematic poles in the Sij or in multiparticle Mandelstams come from the collision zones, where the rational part has logarithmic singularities. But in presence of this Park-Taylor factor, this is a regulator like pulling down 1 over alpha prime Sij. Or maybe a nesting of alpha prime square, Sij, Sijk, and so on and so forth. Okay, I was about to deliver now the BCJ part of the relations. So not only that shuffles annihilate the color ordering, but also these S brackets annihilate the color ordering. And this time I can give you, this time I can pinpoint the origin, unlike the case of super Young-Mills. So where does this S bracket relation or the BCJ relation come from? This can be traced back to a property of the Park-Taylor factors. Suppose you feed the Park-Taylor with a pure S bracket of non-empty words P and Q. Then together with the Kober-Nielsen factor, I'm sorry, I haven't introduced that. So here, all these absolute values with Mandelstam exponents will be referred to as Kn. And this S bracket turns out to give you a total derivative, even a linear combination of total derivatives with respect to various CJs, namely total derivative Park-Taylor P, Park-Taylor Q, and the Kober-Nielsen factor itself. And it's a linear combination where J runs over all letters in the word P, or by translation invariance, equivalently all J's in the word Q. So this S-bracket combination is 0 because the integrand conspires to a total derivative. So imagine you place Park-Taylor with an S-bracket, you convert it to total derivatives, and they will all integrate to 0, as we don't really have a boundary to M0n. Perhaps up to some epsilon-sized circles around the diagonals, but the Kober-Nielsen factor is kind enough to kill the boundary terms. So this BCJ relation holds because total derivatives integrate to 0. Yeah, so this is how KK and BCJ relations have an extension to all orders in alpha prime. And I didn't even need to tell you anything about this anti-holomorphic part other than being permutation invariant. Okay, and now I should fill that shameful gap and now give you some minimal information about this permutation symmetric thing E. So this anti-holomorphic quantity, where all the polarization info is sitting, can be expanded in terms of Young-Mills trees. I hope this doesn't sound tautological to you. We are after a gauge amplitude, but we are after a string theoretic object, which is a funky function of alpha prime. And we are expressing it in terms of a considerably simpler field theory quantity, namely a bunch of Young-Mills trees in some ordering. For instance, I fix 3 of the legs, 1 and n minus 1 and n, and I sum only over permutations R of n minus 3 legs. So there's a double sum over permutations of n minus 3 legs, namely those here. And what else do we have? We have Park-Taylors. Park-Taylors depending on another such permutation Q, 2, 3, 4, and many others. And then we have a kind of intersection matrix in here, or more precisely, as shown in Sebastian's work, this is the inverse of an intersection matrix for co-cycles and has the nickname KLT matrix. Yeah, maybe I should drop these comments right now. This is a matrix of size n minus 3 factorial times n minus 3 factorial. It's more precisely the field theory incarnation of the KLT matrix. There's also a string theoretic one, which was frequently mentioned in Thomas Lamb's talk. But here I'm only going for the more modest field theory version, where the entries are not trigonometric functions, but instead the entries are just polynomials in Mandelstams of degree n minus 3. Okay, and this is also an expression you can use for the Pfaffian in the CHY formalism when you do gluon and graviton scattering. Okay, so this is the explicit form of that E. This is to be, first of all, giving you the complete information, but also this is my excuse to discuss a bit more the KLT matrix. So after all, this talk is an homage to the S-bracket, and the KLT matrix is yet another important object which has a natural representation in terms of S-brackets. So here is more information on the KLT matrix, how the S-bracket is your friend to generate the explicit form of these polynomials. So this is again a result from Hadley's paper from December 2020. Namely, the result goes as follows. So as you saw here, there are two permutations entering this KLT matrix, Q and R. Let's assume them to be in the same alphabet. And this I can write as the inner product of words with a lot of S brackets here and some Lie polynomials there. Okay, clearly I need to define a couple of objects. So perhaps we start with this angular bracket, comparing words A and B. This is, if you wish, the Kronecker delta on words, which is 1 if the words are equal and 0 otherwise. And then what is this fancy L doing? These are complete bracketings, namely left bracketings. Complete. Okay, so first of all, in the right entry, you see an L with square bracket. So the square bracket alluding to commutators. And this L instructs you to do nested commutators, where all the brackets pile up on the very left. So this is producing Lie polynomials for you. Okay, and now wouldn't it be fun to do the same thing with alternative brackets? For instance, the S bracket also has a right to be completely left nested. So this is what's happening in the first entry of this inner product of words. So here we have the complete left nesting of S brackets. Okay, this is a good moment for a sanity check. I was promising you polynomial degree n-3 in the Sij. And note that the Q's and R's have n-3 letters. Now, suppose you know that you are going to stick in an n-3 letter word here. Then the nested brackets will give you a total of n-3 pairs of such curly brackets. So the total number of S brackets that you will see is n-3. And since each S bracket by definition injects a Mandelstam invariant, you still see it, we clearly generate a total of n-3 powers of Sij. So hence the promised mass dimension works out. Okay, so this is how the KLT matrix in the capital E part of that integrand is also winding down to some combination of S brackets. Yeah, maybe I should have said this earlier on. The S bracket is, as demonstrated by Hadley and friends, a Lie bracket. So what is the main content of that statement? First of all, in order to sell it as a Lie bracket, we need antisymmetry. And here it's again important to refer to the dual of Lie polynomials. If you look at the example here, is this antisymmetric over here? Doesn't look like, but importantly, this antisymmetry only holds within this quotient modulo shuffles. So I'm regarding two words as equivalent if they only differ by pure shuffles. And it's a good idea to do that while we are discussing these tree amplitudes here, because shuffles annihilate the Park-Taylor factors. So there's a good reason to work also as a string theorist within this L star space. Okay, so this is check number 1 for Lie bracketness. And then the second check is Jacobi identity. So let me start with a more modest version of Jacobi identities, checked by Hadley and friends. So if you do this twofold nesting and sum over cyclic permutations as you do it in Jacobi identities, then it's easy to verify that this gives 0. And of course, you could roll your eyes and say, it's boring if you only have 3 letters. So what's the more general form of Jacobi identity with more than 2 letters? So now imagine you have some words P and Q with a single letter I in between. Then a more exciting Jacobi identity, which is verified, goes as follows. You have total left nesting with the ordinary commutator operating on the word P, and then you have a total left nesting on S brackets here in the outermost L curly bracket. Okay, so this Jacobi identity is also something one can derive from the recursive definition of the S bracket. Okay, so this is, first of all, completing some properties of the S bracket, and secondly, showing you an application of the S bracket to trees of the heterotic string. A first application was to tell you about the amplitude relations as you dial through different choices of the color ordering P. And a second application was to elaborate more of the structure of the integrand, where apart from Park-Taylor factors, there is this KLT kernel, which by itself has a natural S bracket formulation. Yeah, so this finishes what I wanted to say about the heterotic incarnation of string amplitudes. And also it finishes the discussion of properties that you can already see at the integrand level. The rest of the talk will go towards integration. Is there any question at this point before I start integrating? Okay. Oh yeah, and I should drop a warning. Maybe some of you associate gauge amplitudes in string theory with open strings. And indeed, many string theory courses will start telling you about gauge bosons coming from open strings, or the type 1 superstring theory. But here I took the heterotic string theory, one of the 5 consistent superstring theories. In fact, it's a Princeton production. Heterotic string was invented more or less here, Gross, Harvey, Martinek, and Rome. Yeah. So the open string incarnation of gauge amplitudes will have different relations, certain alpha prime deformations of KK and BCJ relations, known to the experts as monodromy relations. So what you just heard is specific to the heterotic string. But the things that I will say about integration and alpha prime expansion will make a little bit of contact with open strings. So I will argue that the S bracket also has something non-trivial to say on doing these M0n integrals and generating alpha prime expansions. And an additional piece of artillery that I need for that is the so-called KZ associator that will appear a little bit later than the S bracket. Okay, so we have seen a nice integrand for heterotic string amplitudes of any number of gauge bosons. And in order to integrate, we really have to do complex integrals. Each mark point on the sphere, for each mark point there's a d square z. I personally find d square z integrals harder than line integrals, dz. So as a stepping stone towards the sphere integrals, I will do this at the level of a slightly simpler problem. The expansion of sphere integrals will be reduced to those of disk integrals. And there are 2 ways you can do this recycling. So disk integrals fall into the simpler category that I informally refer to as dz integrals. The picture is this, that you have a disk with a couple of marked points on the boundary. You again have the Möbius transformations you can use to send your favorite triplet to 0, 1, and infinity. And then if you are able to integrate over the remaining points over the disk boundary, then there are 2 methods to uplift those disk results to the sphere integrals. One is quite old, Kawai, de Wellen, and Tai 86, which more or less tell you that squares of disk integrals assemble the above sphere integrals for you. That's one way why it's sufficient to do disk integrals. And the other one is, if you are more number theoretically flavored, you can use the single valued map, which is discussed in a series of papers starting from 2012. So it's for these reasons that I will content myself to performing disk integrals now. And one of the two recycling procedures will give you back the information on the alpha prime expansion of the sphere integrals. Okay, to translate all of these words into a concrete mathematical expression, so the kind of integrals I want to solve, and that hopefully correspond to the picture, is we integrate over the disk boundary, which I find convenient to send to the real line. So all of the n-3 integration variables after SL2 fixing, yeah, they will be strictly ordered on the real line and squeezed in between 0 and 1. Call me a coward, but I like it if my integration domains are bounded by 0 and 1, even though this is Möbius equivalent to infinity. Okay, and here is a Kober-Nielsen factor similar to the one on the sphere. Strictly speaking, the exponent is reduced by factor of 2, but this is probably not the big deal. Yeah, and the Park-Taylor factors are an evergreen. So also on the disk, I will be interested in Park-Taylor integrands. One formal reason why is results of Aomoto from the 80s that were mentioned before, saying that Park-Taylor factors span the twisted cohomology, where the twist is this Kober-Nielsen factor. Yeah, so it's even sufficient to go for n-3 factorial Park-Taylor orderings, for the same reason as you heard it before. There are KK relations, there are BCJ relations, so putting all of them together, only n-3 factorial of them are independent. For instance, the one I'm using here. So note that the P on both the left-hand side and the right-hand side is a permutation of 2, 3, ... n-2, which is indeed giving you the promised n-3 factorial counting. Yeah, so this is the integral I want to get done before the end of this session. And well, one approach would of course be to do direct integration using polylogs and more. But here I want to discuss an indirect method, namely, instead of doing the hard integral, find a differential equation that determines the integral for you. And clearly, there is nothing to differentiate in. At least there is no more marked point that I could differentiate in. So to improve that situation, I will deform this gadget here. We do a deformation by an extra marked point, which wasn't there in the original problem. Let's pretend there is one more marked point on the disk, on its disk boundary to be precise. So let's say that I cut off my integration domain here with an auxiliary point. And these points, they also want to bring along their momentum. This has to do with the requirement that boundary terms should still be 0 in presence of this deformation. So all this to say, I will for the moment pretend that there was an extra momentum P0. Okay, so the concrete deformation that I'm advertising here is just augment both the Kober-Nielsen factor and the integration domain by this extra Z0. So concretely, we are here doing, iterated integrals, no longer in the unit interval, but now we are stopping already at Z0. Yeah, I guess we should assume Z0 itself to be in the unit interval, but this will be okay from what you will see in a second. Okay, and as I said, the Kober-Nielsen factor is also now talking to Z0. Note that this double product of over I and J starts at 0. That's why I was introducing a momentum P0 before. Okay, and now the choice of Park-Taylor factors is a little bit wider. I argued before that you need all the KK-BCJ relations to go to the spaces. But those will be perturbed by this Z0 dependence in the Kober-Nielsen factor. So I need a larger basis. It's n-2 factorial now. And I'm not sure whether everybody can see that. Perhaps I should write the rest of the integrand over here. Sorry about the suboptimal blackboard management. So this is part of the integrand still. Park-Taylor factors indexed by P and Q, such that the union of P and Q is again filling up 2, 3, ... n-2. Okay, so this is a deformed version of the disk integrals, and that one will do us a huge favor to get the integrations done. Namely, this deformation yn is engineered to interpolate between the disk integrals z at multiplicity n and multiplicity n-1. So all of this is going into the direction of a recursion in multiplicity. Engineered to interpolate. Namely, the raison d'etre for these yns is that in some limit, you want to have back the zn-1s. And this is, strictly speaking, the limit where the extra marked point, z0, is taken all the way to the origin 0. And then in another limit, z0 going to 1, it will give us back the original integrals that we actually want to do, zn. So each of the yns is interpolating in the way I stated here. And in the moment where we identify the z's, at this moment, we will set the word q to be empty, and we will, in a late stage of the calculation, even set the extra momentum to be 0. So both of these are temporary features that we need to throw away at a sufficiently late stage of the calculation. Okay, what do I mean with this mysterious saying, late stage of the computation? We should keep Z0 and P0 in the game as long as we study the differential equation with respect to Z0. So the recursion going from n-1 point to n point, this works as follows. We get Zn from Zn-1 by integrating the first derivative. Yeah, fundamental theorem of differential calculus. Z of 1 is obtainable from Z of 0 plus the integral of its first derivative. So we will be interested in the differential equation with respect to Z0. And it's a nice type of differential equation. It's a Kniesznik-Samolotchikov one. Namely, if you hit all the integrals y with a Z0 derivative, then after a bit of IBP, you can peel off this differential operator here, the KZ connection, if you wish. And what is the mysterious vector arrow doing? It just instructs you to put together all the choices for P and Q. Remember, for each choice of P and Q, such that their union is covering 2, 3, ... n-2, for each such pair, there's a separate component y. And taking all of these components together, this is enough material to fill an n-2 factorial vector, indexed by pairs of P and Q. So if this is a vector of size n-2 factorial, then the E0 and E1 are n-2 factorial square matrices. For each multiplicity, there's a separate pair of such matrices. And the entries are now linear in Mandelstams, linear in alpha prime Sij. Okay, this is extremely useful because maybe some of you can already anticipate, for those who do a lot of differential equations, I need the path-ordered exponential of this KZ connection to relate n-1 points to n points. So once we have the explicit form of E0 and E1, you can integrate this first-order equation. I will say more about that as time leaves me opportunity to, but I should by all means prioritize the S-bracket aspects of all of that. Yes? So I'm slightly lying. Before I can take a meaningful z to 0 limit, I must compensate with the monodromies by taking a factor of z0 to the power minus e0. So this product is monodromy free and can be evaluated like such. And same for here. It's strictly speaking a regularized limit, which is hidden in between the lines. So I again kill the monodromies by multiplying with z0 minus 1 raised to the power minus e1. Then you are fine. This simply means that later on, the path-ordered exponential is also endowed with shuffle regularization, and that's the defining property of the KZ associator. Yeah, don't worry if these words didn't ring much bell to you. This was not the main focus of what's coming next. Yeah, so our leftover homework is to compute these matrices E0 and E1. The name of the game is take the Z0 derivative of that integral here. So clearly, you clearly take derivatives at the level of the Kober-Nielsen factor, many Z0s in here. So yeah, you will have to process the derivative of the integrand and rewrite the result in the basis we have started with. So I think I will be done in the horizon of 5 minutes, if this is okay with the chairman. Thank you. So we will get the entries through the procedure I just outlined. So this is actually part of the unpublished material, work in progress with Hadley, Carlos, Carlos Rodriguez. So here I'm using a shorthand for saying, take this Kober-Nielsen integral which defines the y vector. So I'm violently putting all of this into a shorthand that goes like integral of gamma 0 tensor kn. Yeah. So just to save myself some writing word, all of this is now in that shorthand. And yeah, for a given choice of Park-Taylors with words P's and Q's, their derivative can be brought into the Krzenicznik homological form as follows. So there's first of all some Mandelstam involving the word P and just the Park-Taylor factors we started from. Oops. Okay, and then there's an extra term coming from the IBPs. If you want to see them in more detail, I have an example in my notes that I can show you in the break. And yeah, most interestingly, there is an S-bracket. More precisely, we have a sum over all deconcatenations of that word P here into smaller words X and Y. And it's the Y word which lands in such a Park-Taylor factor with S-bracket. Yeah, and there's a similar term here for the other singularity in the KZ equation. And okay, this is more or less a relabeling of the previous line. One term where all the Park-Taylor factors are left inert, and yet another term where this time we deconcatenate the Q word and get things like that here. Whoops. Again, an S-bracket of 1P with the second half of the word Y. Okay. So from this result, you can read off what the matrices E0 and E1 are. And this is probably begging for examples. So at 4 points, these matrices are going to be 2 by 2. And they look as follows, not too scary. This is just squeezing out the information which is here. And all the Mandelstams come from the S bracket here. And as I said, you can later in the day set the momentum P0 to 0, namely post-KZ equation. So the only thing you keep in getting alpha prime expansions is the part that doesn't refer to P0. So this is a 4-point example, and that is admittedly the most crazy way to compute the Veneziano factor. All of this will resum after integrating the KZ equation to the old school Veneziano factor, gamma of S, gamma of T divided by gamma of S plus T. So I don't want to argue that this is useful at 4 points. But starting from 5 points, these disk integrals are harder. You need hypergeometric 3f2s and more, starting from 5 points. So there, it's much more pressing to have a multiplicity agnostic method like here. So the only thing that gets worse is that the matrices become a bit more bulky. And for some choice of basis for the P's and Q's that label the Y entries, for some basis choice, a typical E0 at 5 points looks like such. And again, you only need the P0 equals 0 limit. Okay, in view of time, I will just be schematic about where the rest of the story goes. You need these E0s and E1s to integrate the KZ equation. The KZ equation being that one. So by taking everything together, which is on the board, you get essentially the endpoint disk integral from a path-ordered exponential of these KZ connection. So Pexp is meant to be a generating series of iterated integrals where the non-commutativity of E0 and E1 is taken into account. And as I said before, in response to Julio's question, there's a certain regularization scheme inherited from the monodromy relations up here. So maybe we want to write it like such. It's a generating function of shuffle regularized MZVs, also known as the Drinfeld associator or KZ associator. And this, for the number theoretic friends, gives multiple zeta values. Yeah, so from the bigger scheme of things, I think I've covered some subset of the tree-level topics I wanted to present, namely that the S bracket is a universal friend to study relations among gauge theory amplitudes, to secondly, study relations of heterotic gauge amplitudes, to bring the integrand into a good form, but also the S bracket was indispensable in this closed form solution for the braid matrices E0 and E1. So S bracket is also doing integrals for you. And if there was another 20 minutes, I would be talking about a loop level extension of that. So the engine of all these shuffle relations were simple partial fractions among rational functions. So high school mathematics of iterated partial fractions give you everything you want to know about the shuffle relations you saw. And at genus 1, we work with doubly periodic functions on the torus, which are not literally obeying partial fraction. But if I use theta functions to discuss functions on a torus, it's the Fay identity, which will replace partial fraction, and which will again lead to omnipresence of shuffle at genus 1. Yeah, and also at higher genus, there are analogs of Fay relations, not only those among theta functions that you know from the book of John Fay, but also more recently, some Fay identities among integration kernels in a flat connection that Eric Doker and myself described in a recent paper. So there's a lot of use of Fay identities at higher genus to carry over all these shuffle relations. And the work in progress with Hadley and Carlos Rodriguez also involves a genus 1 application of the S bracket. Okay, that's it. Sorry for going over time.